Good afternoon, Professor. How you doing?
Good. How are you?
Just a bit tired, but we're there.
Hang in there. You have you stayed up late working on homework or something?
Yeah, just working on just simple things, and you just get tired. Yeah,
Get some good sleep tonight.
I'll try. Best believe.
I mean, it's a lot easier for me to say this. So I know it's a little bit hypocritical, but the work's always going to be there, but your health and your and your rest is not always going to be there. So take care of yourself when you can.
What about you, Professor? You been sleeping well, or same?
Yeah,
Same.
yeah, well enough. Yeah, I have a cat that wakes me up at like 6:30 in the morning to be fed. So I just adjust my sleeping schedule. I go to sleep a lot earlier. But sometimes if I'm up and the cat wakes me up, then I lose a bit of sleep. But working from home is nice because I can nap in the middle of the day and still be okay.
What type of cat is it?
It's she's a Siamese, so half Siamese, half tabby. Um, she's old, so she and we have to feed her this very specific food because she's diabetic and she only gets fed at like specific parts of the day. So she definitely makes it known when she's hungry. All right, it's 2:30, so let's go ahead and get started. All right, good afternoon, everyone. How's everyone doing today?
Pretty good. Getting a
Good
little
afternoon.
lost on the homework, but I'll figure it out.
Yeah, I got a few questions about it last night. We'll definitely, I think the difficult thing with the homework is that we haven't really seen that many examples yet, at least not on the more complex side, which is what the homework problems are. But today we are going to do some examples that I think should help you out with the homework.
Sweet.
Oh, go ahead.
Oh, I just said sweet.
Oh, yeah. So I think that should help. So I finished writing up the homework yesterday. So and I'm glad that people have already taken a look at it and I've already started, because I think that'll make today's lecture a lot more worth it. So first thing I want to do today is I'm going to do a couple examples. One is a heat equation example, which we're going to take the whole heat equation and integrate it and apply boundary conditions. So that should help you out on problem 2. And then the other example we're going to do today is a thermal circuit problem. And so that should help you out on problems 3 and 4. Okay. And then after that, we'll probably have some time after that. So we'll start the next set of lecture notes, which is on radial systems. And so we'll see how the same concepts that we've been learning apply to cylindrical coordinates and then eventually spherical. Although I don't think we'll get to spherical coordinates today just yet. Okay. And so, the other announcement I want to make is that, in case you haven't seen it already yet, the first homework set is posted. So all of that is, based on lecture note 01, which we're going to finish up today. And so it's going to be due a week from today. And so it's due next Wednesday, which is February 9th at 11:59 p.m. Or if you want to turn it in person, we'll be back in person by next week as well. And so you can feel free to bring the problem set to the lecture room. Right? And that's the other announcement I want to make too, is that the provost just sent an email yesterday saying that we are good to go. And so according to her, then the conditions with COVID are safe enough for us to return to campus just as planned. And so starting next Monday, I will be lecturing from the room, but I'll be continuing on with the Zoom thing. And so if you would like to attend the lectures virtually still, if you don't feel comfortable coming to campus, then that's totally fine. But I will be in the room, and so if you do want to come to the room and and take the notes from there, just so you can interact with me directly, interact with your classmates directly, that's available to you. But the Zoom will still be an option. Okay. Right, and I think that's all my announcements. And so are there any questions I can answer before we get started? Okay, all right, and so let's go ahead and get started. And so on Monday, when we left off, we had just finished talking about thermal circuits, and so that's basically all of the technical and all the conceptual information that has to do with planar conduction. And so today, I do want to start with a couple examples, just so that you guys can get a couple more looks at how those concepts are actually applied in practice. Okay, all right, and so this first example is a heat equation example. Okay. All right, and so in this example, we have we basically have steady state conduction in a plane wall. Right. And what's unique about this that we haven't seen yet is that there is thermal generation. Right, and so basically we're assuming that maybe this wall is laced with a chemical that's reacting, that's producing heat, or maybe it's a material that absorbs heat from somewhere else. Okay, all right. So the diagram looks something like this. Okay. And so here's our planar wall, and just like we've always had, we're viewing a cross section of the wall. Okay. Right. And so on the left side of the wall we have convection going on. Okay. So we have our 3 arrows here that indicates that fluid is flowing past the wall. And so the ambient temperature of the fluid here is about air temperature. Maybe it's a little bit chilly outside. So the ambient temperature is 20 degrees C. And the convection coefficient here is 500 watts per meter squared degrees C. Okay. All right. We also know the thickness of the wall. And so the length of the wall here is 50 millimeters. Right. The thermal conductivity, K, of the wall is 5 watts per meter degree C. Okay. And one more thing that we have, which is actually a little bit unique for this problem. So usually when you have a convection boundary condition, you don't know what the surface temperature is, but in this case we do. And so the temperature of the wall here is, we'll call the TS for surface temperature, is 120 degrees C. Okay. Right. And so on the right side of this wall, if you notice that I've kind of marked that wall with some hash marks, what that indicates here is that the wall on that side is perfectly insulated. Okay. And if you recall from previous lectures, when something is perfectly insulated, that means no heat can escape through that wall. Okay. And so we basically say that the heat transfer rate through that wall is going to be 0. All right. Let's see. I think that's all. Okay. And so what we're interested in solving for here is we want to solve the heat equation for the temperature distribution in the wall. Okay, so that's part A of the problem. Okay, part B says that, given these thermal conditions, we want to solve for how much heat the wall is generated. Okay. Okay. In other words, what we're going to be solving for here is the value for Q dot. Okay. Okay. Right. And so basically, we're going to take our solution for part A, and we're going to take all the boundary conditions that we have on this problem, and then we're going to use that to solve for Q dot. Okay. Because if you notice from this problem, we actually have 3 boundary conditions, which is a little bit unusual. So a lot of times we actually are only given 2, because we only need 2 boundary conditions to solve a second order ODE. But we have an additional unknown, and that additional unknown in this case is the thermal generation. And so because of that, we need three boundary conditions. Okay? And our 3 boundary conditions are basically our insulated boundary condition on the right. We have our surface temperature here on the left, as well as a convection boundary condition here as well. Okay. And so these are the 3 boundary conditions that we're going to use to solve for parts A and part B. Okay. And before I move on, I want to, just because I got a few questions about this last night, I want to draw this distinction between these 2 things. Okay. And so I got a lot of questions that asked me, about problem 2, to ask, is it correct to apply a specified temperature boundary condition when you have convection like that? And I was telling people that it's that would not be correct, because even though we have fluid that's flowing with a certain temperature on the outside of our surface, that doesn't mean our solid surface has the same temperature. And in fact, most of the time they are going to be quite different from each other. And so you can see from here, just from the conditions of the problem, that the surface temperature of the solid is 100 degrees Celsius higher than the fluid. Okay. And the way you could think about it is like this. And so whenever you have a flowing fluid, and so let's take the air for instance, right? the fluid is going to have a certain temperature, and we usually measure that temperature usually somewhere far away. And so if you think about stepping outside on a windy day, right? And so the air outside has some temperature. Right now, according to the weather app on my computer, it's about 64 degrees Fahrenheit, okay? And so the wind is blowing at 64 degrees Fahrenheit. But if you measure the temperature on, on the surface of your skin, it's going to be a lot higher than the air temperature outside, because that temperature is actually in contact with your, with you, the solid, right? And so most of the time, when you do have a flowing fluid, its temperature is going to be different than that of the solid, just because one is in the fluid, which is measured far away, and the other one is on the solid, which is measured right on the surface. Okay. And so that's important. And so, when you have a convection boundary condition, you want to make sure you actually use the convection equation, which we'll go over in this problem, and not use the specified temperature. Okay. So a few people asked me about it, and I think we haven't done an example with convection yet, so it's totally understandable. But I did want to clear that up. Okay. All right. Any questions on the setup for the problem before we start solving it? Okay. All right. So let's start with part A. Since we're looking for a temperature distribution in this problem, okay. Remember, temperature distribution means we're going to solve for a function t of x. That means we know that this is a heat equation type problem. And so let's go ahead and start from the full heat equation. Okay. And so our full heat equation is partial squared T partial x squared plus q dot over k is equal to 1 over alpha partial t, okay? And first thing we're going to do is, just because it said so in the problem, we can go ahead and cross out this term right here, because we're assuming that the problem is steady, right? And so by doing that, since we eliminate the time derivative, then these derivatives here on space become, regular derivatives, okay? All right. And so now that the right-hand side is equal to 0, I'm going to go ahead and move the q dot over k to the left-hand side. Okay, so we have d squared t dx squared is equal to minus q dot over k. Okay. We don't know what q dot is yet, but we are going to assume that it's constant. Okay. And that helps us out a lot because that allows us to basically directly integrate this. This expression. Okay. So we're going to have dx. Okay. And so actually, let me go ahead and write that down. Assume constant. Okay. And so on the right-hand side, we basically just have a number, a scalar, right? And so if we take the integral of both sides, on the left-hand side, we're left with dt dx, okay? And on the left-hand side, we have minus q dot over k x plus c1, right? Because the integral of a constant is just that constant times x. And then since we're doing an indefinite integral, we have to add an arbitrary constant c1, right? And then we're going to integrate this one more time in order to get t of x. Right. We integrate one more time. Oops. We integrate one more time and we get minus q dot over 2k times x squared plus c1 times x plus c2, right? Where again, the c2 comes because, we're doing an indefinite integral and we have to add our arbitrary constant, okay? All right, and so here is our general solution. Okay, general solution to our ODE. And we have three unknowns here, right? So we have q dot, which is an unknown, which we're going to solve for in part B, C1 and C2, okay? And so we're going to use our 3 boundary conditions to solve for those values. Okay. All right. And so on the next page, I'm going to write out our 3 boundary conditions in mathematical form, and then we're just going to simply apply that to the equation, in order to get its value. Okay. Any questions on this? Okay. All right. And so, we have 3 boundary conditions in this example. Okay. All right, so our first boundary condition is a specified surface temperature at x is equal to 0. Okay. And remember that surface temperature was Ts is equal to 120 degrees C, right? And so in mathematical form, the way that we can express this is we can say that our temperature distribution at x is equal to 0 is equal to 120. Okay.
Is this for part B?
This is still part A. And
Okay,
so part A, we're still solving for, C1 and C2.
Gotcha.
Mm-hmm. So this one's actually really easy to apply. And so let's go ahead and apply this one first. And so usually, this is not a I should say, not a formal textbook way to approach these problems, but it's a good kind of trick. Usually, whenever you have a general solution here that depends on x, like we have here, applying the boundary condition at x equal to 0 is usually a good first way to go, because a lot of terms are just going to cancel, right? Especially if it's a specified temperature boundary condition like this. Okay, and so let's go ahead and apply this right away because we know a lot of terms are going to cancel. Right? All right. And so if we go back to our general solution, right? And so our general solution was minus q dot over 2k times x squared plus c1x plus c2. Okay. If we apply this at x is equal to 0, where we're basically going to apply plug in 0 at every location that we have x, right? And so we have 0 here, 0 here, right? And of course, that's going to cancel out all of those terms, because we have 0 times a constant, which is 0. Okay. And according to the boundary condition, if we apply x is equal to 0, then we're going to get 120 degrees C. Okay. And so we can see right away, because most of the terms are canceling, that C2 is equal to 120 degrees C. Right. And so that's good. Okay. And so just by the direct application of one boundary condition, we get one of the constants really, really easily, which is not always the case. Okay. Okay. All right. And so that's the specified boundary condition at x equals 0. We actually have a second boundary condition at x is equal to 0, which is a little bit unique. And so usually you don't have more than one, but in this case we do. Okay. Right, and that second boundary condition is a convection type boundary condition, right? And so when you have a convection type boundary condition, you don't set the temperature equal to a specified number. What you say is that the amount of heat that's leaving the surface via conduction is equal to the amount of heat that's being accepted into the fluid via convection, right? And so it's a balance between conduction and convection, right? And so for the conduction side, we have we have Fourier's law, right? And so what we say is minus k times a times dt dx, okay, at x is equal to 0, right? And so this side of the equation here is conduction, because it's, again, Fourier's law, right? And so the other side of the equation here is going to be our convection, right? And so for convection, we use Newton's law of cooling. And so for Newton's law of cooling, we have H times A times T infinity minus t at 0. Okay. And so when you have a convection type boundary condition, we have to set both of these equal to each other. Okay. And the key thing to notice here is that for these two entities right here, we're going to plug in our general temperature solution. Okay. All right. And so let's go ahead and plug these in. And so the good thing about the right-hand side here, t at 0, we already know what that is because we solve for it on, in condition 1. And so we know that this one right here is 120 degrees C. Okay. And so the only goal here is to plug it in for the other one. Okay. Okay. All right. And so if we go ahead and take the derivative of our general solution, the derivative of our general solution is minus q dot over k times x plus c1. Okay. Right. And so if we apply this at x is equal to 0, then that first term is going to go away, right? And so all we're left with on that side of the equation is just c1. Okay. All right. So let's go ahead and plug all this in. And let's also cancel out these a's because we have an a on both sides. Okay. And so we have minus k times c1 is equal to h times t infinity. T infinity here is 20 minus 120. Okay. We're also given the values of k and h from the problem. And so k here has a value of 5 watts per meter K, or excuse me, per meter degree C. Okay. And H here has a value of 500 watts per meter square degree C. Okay. And those are given to us directly into the problem. Okay. All right. And so the only thing left here is that, the only unknown we have in this equation right now is C1. And so we can go ahead and plug all the values in and solve for the value of C1. Okay. All right. Any questions on how we applied this convection boundary condition?
I had a question, Professor. Could you
Sure.
go over one more time why you use a negative q dot over kx plus c1?
Negative q dot, or which one? Negative q. Oh, go ahead.
When dt over x is equal to negative q dot over kx plus c1.
Sure. And so that that's simply just the derivative of our general solution. And so our general solution is this one here from the previous page, right? And so all I did was I just took the derivative of this expression with respect to x.
Oh, okay, so that's the dt of x. That's what that's equal to. Gotcha.
Exactly. Yeah. And actually, if you because the way that we got this is through integrating our heat equation, you can see that we actually have the expression for dt dx right here on the spot, right before we got to our general solution. So yeah, just plug that in on that side.
Thank you.
Yep. Mm-hmm. Okay, so let's go ahead and finish plugging in the numbers here, and we can solve for C1. Okay. And so if we finish plugging in the numbers, we have a minus 5. C1 is equal to minus 50,000. Right. And so this tells us that C1 is equal to 10,000. And the units for this is degrees C per meter. Right. And so now that we have 2 of our constants here, we're done with part A of the problem. Okay. And so the last thing that we have to solve for here is the value of q dot. Okay. All right. So now that we have our 2 constants here, let's go ahead and apply our third boundary condition. And so now we're doing part B. Okay. And so our third boundary condition, remember, was an insulated surface at x is equal to L. Okay. All right. And so an insulated surface is a special type of boundary condition or special type of condition of a heat flow boundary condition, right? And so remember, whenever we have a heat flow type boundary condition, we are going to use Fourier's law, right? And so what we're saying is the heat flow at that surface, you know, and another way to express that heat flow is to plug in for Fourier's law, okay?
Dr. Chen,
Yep.
why do we use Fourier's law for this case?
Yeah, so we use Fourier's law because Fourier's law connects the heat transfer rate, or Q, with our you know, with our temperature distribution. And so for our third boundary condition, you know, we have an insulated wall on the right hand side. And so when we have an insulated wall, that tells us that Q, little q, is going to be equal to 0 over there. And so the way that we connect this with our temperature is we just plug in for Fourier's law right here.
Okay, got it.
Yep.
Thank you.
Mm-hmm. All right. And this is all going to be equal to 0 because of the insulated wall. Okay. All right. And so let's go ahead and plug that in. And so right now we have minus k times a. And actually, you know, because we have 0 on both sides, we can go ahead and divide by k times a on both sides of the equation. Okay. And so that's going to cancel those out, right? And so we have simply dt dx at x is equal to L is equal to 0. Okay. If we plug in our expression for dt dx, which is minus q dot over k times x plus c1. Okay. We have c1, and so c1 is 10,000, right? And in this case, we're going to plug in x is equal to L, where L in this case, let me go back and see, is 50 millimeters, where 50 millimeters is 0.05 meters. Okay. All right. And then we can go ahead and solve this expression for q. Okay. All right. So we plug everything in. We get minus q dot all over k, where k is 5 watts per meter degree C. Okay. Times 0.05 meters. This is equal to minus C1. And so that's minus 10,000. Right. We go ahead and manipulate this expression. We solve for q, and we see here that q dot is equal to 1 million watts per meter cubed. Okay. All right. And so now that we've worked through everything in the problem, we can go ahead and plug it all back in. Okay. And so we plug it all back in, and we get our full temperature distribution, right? And so our full temperature distribution is minus 1 million x squared plus 10,000 x plus 120. Okay. Yep. All right. And so that's an example of using our heat equation for, you know, a problem like this. So, you know, this one was, you know, quite a bit more steps to it than our previous example. So, you know, hopefully this gives you some help with doing problem 2 on the homework. Any questions on this? Yeah, we do, and yeah, that's right. So there should be 1 less 0 here. Yeah, because k is 5, and so we divide by 2k. That's divided by 10. So yeah, thanks for catching that. Yeah, I have a typo in my notes. Mm-hmm. Okay. All right, and so that's an example of a heat equation type problem. And so now let's do a more sophisticated thermal circuit type example, just to help you out with problems 3 and 4. Okay. All right. All right, and so in this situation, we have a kind of a chemical manufacturing kind of example. Okay, and so in this situation, we have a film. You can think of a film as like a thin slide of glass or something that's trying to be bonded to a substrate. Okay. Right, and so this upper part right here is a film. Right, down here is the substrate. Okay, and these two want to be bonded together, right? And so basically, we want to form a connection in between these two, right? And so to do that, the interface in between the film and the substrate is being heated with a heat flux. Okay. And I don't think we've discussed what heat flux is, and so I'll make sure to talk about that once we get there. Okay. And so basically, what's happening is that the laboratory is applying some kind of radiation to heat that interface between the film and the substrate. Okay. We know the thicknesses of these two layers, right? And so we'll call that thickness LF for film. And then we'll call that thickness LS for substrate, okay? And on top here, we have heating via convection. And so there's gonna be a T infinity and an H there, okay? And then we're going to assume that the bottom of the substrate is being held at a constant temperature, T1. And let me just go ahead and give you all the numbers for these variables. Okay, so LF is going to be 0.25 millimeters. The thermal conductivity of the film, it's very insulating, and so it's made of some kind of glass material most likely, because its thermal conductivity is only 0.025 watts per meters Kelvin. Okay. The thickness of the substrate is 1 millimeter. And the substrate is also made of a fairly insulating material. And so it's 0.05 watts per meter Kelvin. Okay. Right. All right. And so what else, the other things that were given here, T1, the temperature at the bottom of the substrate here is going to be 30 degrees C. Okay. The temperature of the air, T infinity, this is going to be, 20 degrees C. And the convection coefficient of the air is 50 watts per meter squared Kelvin. Okay. All right. Right. The other piece of information that we're given in the problem is that in order for the bonding to occur, then the interface between the film and the substrate must be maintained at a temperature of 60 degrees C. Okay. And since the interface between the film and the substrate is at a higher temperature than the air and the back temperature, what's going to happen is that heat is going to start leaking out, up and down, between the film and the substrate. Okay. And so in order to keep maintaining that temperature, we have to apply some kind of heating to that interface, right? And so our objective in this problem is to solve for how much heating that we have to apply. Okay. And in this case, because we have multiple layers to this problem, we're using a thermal circuit is going to be the most efficient approach. Okay. All right. Any questions on the problem setup?
So heat just seeps out because it's too hot, right?
Exactly. Mhm. All right. Okay, so let's go ahead and start solving the problem. But actually, before I do that, let me give you the definition for heat flux, because I forgot to do that last time. Right, so you'll hear the term heat flux quite a bit, especially if you're going to look through the textbook. Right? And so heat flux is basically just a different way to express heat transfer rate. Okay. Right, so heat flux is basically just an expression of heat transfer rate divided by area. Okay, it's kind of very similar to the relationship between force and pressure, right? And so pressure is just basically a force that's distributed over an area, and so heat flux is kind of the same thing. And so it's a heat transfer rate distributed over an area. Okay, and so the most common symbol you'll see for heat flux is usually it's given the double prime sign, right? And so the relationship between Q double prime and Q is that Q double prime is equal to Q divided by A. Okay. So that's all that heat flux is. And so heat flux is simply just little q, and we just divide it by A. Okay. All right. And so let's start with part A. And so part A of the problem is we're going to draw the thermal circuit that represents the situation. Right. And we have 3 resistors here because we have the 2 solid layers, and we also have convection, right? So we're going to draw 3 resistors. Okay. And so we'll call this resistor our air, okay? Because this is the convection resistance of the air. This is going to be the conduction resistance of the film. Okay, and then that resistor is going to be the resistance of the substrate. Okay, and so let's go ahead and fill in the values for these resistances. Okay, right. So remember, convection resistance is just going to be 1 divided by H times A. Right. The film resistance here is just going to be LF divided by KF times A. And then the substrate resistance is just LS divided by KS times A. Okay. All right. And the next thing we're going to draw in is the interface between the film and the substrate, because that's where things are going to take place. Okay. Right. So we know from the problem that the temperature of this interface has to be 60 degrees C. Right. And the heating is going to be applied on this node as well. Okay. Right. And the last thing I'm going to fill in on the circuit here are the end temperatures, right? And so when we go from the interface down to the bottom of the substrate, we're going to end up at the substrate back temperature, and so that's T1, right? And so if we go from the interface between that and we go through the substrate, the temperature of that node there is T1, right? Whereas if we go the other way, and so if we go upwards past the film and past the convection layer, then we end up at T infinity, right? And so the other end temperature here is going to be T infinity, right? Right. Any questions on how we constructed that thermal circuit? Okay. All right. And so now that we have the thermal circuit constructed, we can now use that to actually compute the amount of heat that's going in both directions, right? Because if we connect this to the figure, right, because this node right here is a higher temperature than T1 and T infinity, heat is just naturally going to go in those directions, right? And so we're going to apply two calculations on the circuit, which accounts for heat going in each of those directions, right? So let's compute the heat that goes right first. And so this is going to be the heat loss to the substrate. All right. And so if you remember, the way that we compute heat transfer rates from a thermal circuit is we take a difference of the temperatures, okay? And so in this case, we take a difference between 60 degrees C, which is the nodal temperature at the interface, minus T1, where T1, what was T1? T1 was 30 degrees C. And we divide by the resistance in between them. And so the only resistance that's between our interface node here and the substrate node, we only have that single resistance of the substrate, right? And so we're going to divide this by Ls divided by Ks times A, okay? And this is equal to Qs, or Q substrate, okay? Right, and we have basically everything here to compute what that QS is. Okay. But before I do that, actually we don't have one thing, and that one thing is the area. Okay. And so in order to get rid of the area, I'm just going to divide both sides by area. Right. Right. And so on the right hand side, because we divided by area, this becomes a heat flux. Right. And so this becomes Qs double prime. And then this area right here, because we're multiplying it by the denominator, is just going to cancel out with that area right there. Okay. So that's kind of a neat little trick where if you're not given cross-sectional area in the problem, you can just solve it in terms of heat flux, and you can just divide by the area in order to basically just get rid of it. Okay. All right. Any questions on this so far? Okay. All right, and so we have everything else here because we're given both Ls and Ks from the problem, and so if we just plug those in, right, and so we plug both those in. Oh, sorry, question? Yeah, I can go back for a second. Mm-hmm. Okay, you good? Okay. All right, so we plug in for Ls and Ks, and I don't have those numbers here actually in front of me. And so I'll just say dot, 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 right? And so if we plug those in, we get Qs double prime is equal to 1500 watts per meter square, okay? Right, and so that's the heat loss that goes through the substrate, okay? Now let's compute the heat loss to the air, right? And so if we go back to our thermal circuit here, right? So the heat loss to the air, right? We start again at our middle node here, 60 degrees C, and then to get to the air, we actually pass through two resistances here, okay? And so our Q air here, so we'll call that QA, this is equal to 60 degrees C minus T infinity, where I believe T infinity is 20 degrees C, am I correct? Yes. Right, and so T infinity here is 20 degrees C, okay? And we cross over two resistors here, right? So first we cross over the convection resistance, 1 over h times A, plus the film resistance. And so this is LF divided by KF times A. Okay. Right. I'm going to do the same trick I did for the substrate. And so I'm going to divide both sides by A. Okay, just to get rid of the A's down here, just because we don't really know it. Okay. Right. And so we get QA double prime is equal to 16 minus 20, which is 40, divided by the thermal resistances. Okay, so we have 1 over H plus LF over KF. Okay, where we're again, we simply plug in for everything on the bottom because we're given the convection coefficient and we're given the all the parameters for the film. Okay, and if we plug all those in, we get QA double prime. This is equal to 1,333.33, repeating of course, watts per meter squared. Okay, right. And so that's the heat loss to the air. Okay, and so now that we have the heat loss to the substrate and heat loss to the air, we know that our applied heat, which is Q naught double prime, has to basically balance these two out, right? And so our total amount of heating that we have to apply is just going to be the sum of these two things together, okay? And so finally, what we can say is Q naught double prime is equal to QS double prime plus QA double prime, okay? Right. Because in order to maintain 60 degrees C, then we have to basically balance out all these heat losses, okay? And so we add them together, we get 2,833.333, repeating of course, watts per meter square. Okay. And that's the answer to that example. All right, any questions on this example here?
The Q naught is the heat needed.
Yes, that's the heating that we're applying. Because if you remember from the problem statement, we're applying basically a heating to this interface between the film and the substrate, and so that's basically the value or the magnitude of the heating that we're applying.
Quick question, Professor.
Sure. Mm-hmm.
So our K's and H's were in terms of Kelvin, but our temperature was in degrees Celsius. Did we take that into account?
Yeah, no, that's a great question. So those two can actually be used interchangeably, because the conversion between the two is just a simple addition, and so you can use those interchangeably. Sometimes I did get a little bit lazy here because if you want to be more clean, it should all be in terms of the same thing. But I think here I just kind of read it straight off my example, which had Kelvin. But yeah, if you do want to be more clean, you can just convert all the Kelvins to degrees C. Yeah. Okay. All right, and so that's our thermal circuit example. And so I think that should hopefully help you out with problems 3 and 4 on the homework. Okay. All right, and so that does it for our first set of lecture notes. And so that's planar conduction in the books. Okay. And so we have about 25 minutes left in class. And so I do want to start the next set of lecture notes, which is conduction in radial systems or polar systems. Okay. Oops. Pass this one now. All right. And so I think this is the this is the part of the class which I think initially seems really scary to people, just because it's only week 2, and I think if you guys kind of feel the same way I did back when I was in college, cylindrical coordinates, polar coordinates, spherical coordinates, it always scared the shit out of me. And so to already kind of see that in week 2 is kind of intimidating. But what I'll show you is that a lot of the intuition and a lot of the methods that we've already developed in the last 2 examples, we can just apply those directly to radial systems The only thing that's different is just that our heat equation just takes a slightly different form, and our thermal resistances have a different equation as well. But all the same intuition and stuff still applies. Okay. All right. And so what this section is going to be about is quantifying or computing conduction in systems with a circular shape. Okay. And so first we're going to look at cylinders. And so we're going to work in cylindrical coordinates. And then later on, we're going to do spheres, probably next week. Okay. And so even though these systems are technically two-dimensional, right? And so if we draw kind of a cylinder, okay. Right. And so if we think about the heat flow through the cylinder, it's going to be coming out just like that. Okay. And so, now we have Q that's coming out kind of this way, just like that. Okay. If we were to look at this system in terms of Cartesian coordinates, we can see here that the heat flow is actually in two dimensions, right? So we have some that's going the X direction and the Y direction, right? But if we switch our coordinate systems to polar coordinates, we actually see that this is actually a one-dimensional heat flow as well. And 1D is great because 1D means that we can actually solve. Okay. All right. And so let's just go ahead and get this out of the way. And so I'm going to go ahead and give you the heat equation in cylindrical coordinates. And don't be alarmed just yet. It is a little bit intimidating, but we'll simplify it a lot with our assumptions. All right, so we have 1 over R partial R times K times R partial T partial R, okay, plus 1 over R squared partial theta times partial theta of K partial T partial theta, right? Where theta here is our polar coordinate. Okay. Then we have the axial component, which is Z. So you have partial Z of K partial T partial Z. Okay. Plus Q dot, which is our thermal production term, plus rho Cp, where Cp here is heat capacity, multiplied by partial T partial T. Okay. Right. All right. And so that's our full heat equation in cylindrical coordinates. Okay. All right, so I'll give you a couple of seconds to write that down. But what I'll show you is that there's actually a lot of similarities between this equation and and our Cartesian one. Okay, it's just looking at what terms kind of correlate with the other terms.
What does the P stand for in the Q dot equals P in the bottom?
Q dot. Oh, so that's a rho. So that's density. Yeah, I think in the previous I think in the previous heat equation, I divided this by K and we got 1 over alpha. But, you know, I'm leaving that there for now just because we're not going to do, I mean, we're going to assume steady state. So that entire right-hand side is going to go to 0. But we'll do unsteady convection in a later week. Okay, and so let me go ahead and connect. Let me show you how these terms actually connect with each other, or connect with the Cartesian heat equation, which we just got finished, talking about. Right. So all these terms here actually go together, right? And what they all represent is this represents spatial diffusion of temperature, right? Okay. Remember last week we talked about what diffusion means, and so all that basically means is that temperature is just going to spread out equally in all directions. Okay, and so what all of those terms in the equation, that's what they represent. So they represent the fact that even though you're in polar coordinates, heat is still going to do its thing, and so it's still going to spread out kind of equally in all directions. It's just that when we look at the problem or we quantify in terms of polar coordinates, we have to make some adjustments, based just because the coordinate system is different. Okay. Right. So those are the spatial diffusion terms, and those are the terms we're going to work with the most, when we're solving problems. Right. We have our Q dot term, and so Q dot here remains the same, and so this is our thermal production. Okay. And then finally, what we have here, because we have the time derivative, this is our unsteady term, okay, which we're going to neglect for now because we're just doing steady state conduction. Okay, but I did want to show it to you in all its full glory, just so that you can always have it as a reference. Okay. All right. And so now let's talk about some of the assumptions that we're going to make. Okay. Because we can't solve this equation in its entirety just yet. Okay. All right. And so the first assumption that we're going to make, okay, of course, is going to be the steady state assumption. And so the steady state assumption is going to cross out the unsteady term, and so we're just going to get rid of that guy. Okay. The next assumption that we're going to make here is the axisymmetric assumption. And all that basically means that any derivatives with respect to theta is just going to go down to 0. Okay. And so if we look into the diffusion term, we have a term here that has a theta derivative. Okay. And so we're just going to cross that term out. Okay. Okay. And the last assumption that we're going to make is we're going to assume that our temperature does not depend on Z. Okay. Okay. And so that means that any derivatives with respect to Z is also going to be 0. Okay. And so if we look at our equation here, I know it's a little bit messy right now, but we can see that our third term right here has a derivative with respect to Z. Okay. And then we're also going to cross that one out. Okay. And so all that we're left with here is just 2 terms. So we have the term that depends on R, and we have our thermal generation term. Okay, or thermal production term, excuse me. And so I'm going to clean this up, and then I'm going to write it, the equation that we're mostly going to be working with on the next page. And then I think we have time for one more example today. Okay. All right. Any questions on this so far? Okay. All right. And so after applying all those assumptions, we're left with, just a couple terms left. And those terms, they correspond to the 1D polar heat equation. And so this is the one where we're going to start with to solve problems. And so that equation should be 1 over r ddr, right? I'm converting the partial derivatives to regular derivatives here because we've gotten rid of all the other partials, okay? And so we can use d instead of partial. Okay. Right, so 1 over r ddr of kr dtdr plus q dot is equal to 0. Okay. And of course, if you have a situation where you can assume no production or no generation, you can go ahead and get rid of q dot. But if you do have it, then that's where it goes into the equation. Okay. All right. And so now that we have this expression here, let me go ahead and write out the polar version of Fourier's law. Okay. Where if we want to compute the heat transfer in the radial direction, okay. Okay. And so it's going to look very similar to our Cartesian one. And so we take the product of the thermal conductivity, K, multiplied by area, multiplied by dTdr, okay? But we can actually take this one step further because, we know a little bit more about our geometry. And in particular, I'm going to plug in an expression here for A, right? So remember, A here is the cross-sectional area at which the heat is actually passing through, right? For a cylinder, which is what we're going to be looking at right now, we can actually come up with an expression for that surface area of a cylinder, right? Okay. And so if we take 2 pi times r times L, L being the length of the cylinder, this is the surface area of a cylinder. Okay. And so, if we have a cylinder that looks like this, right? This is R being the radius, and the length of the cylinder is right there. Okay. And so you can see here that 2 pi r is the perimeter of the circle, and then L is the length of the cylinder. And so if we multiply those two things together, we get the surface area of this cylinder. And so, when we're in cylindrical coordinates, we have a little bit of a more specific definition for Fourier's law. And so we can say this is equal to minus k times 2 pi r times L dt dr. Okay. And so that's a little bit more of a specific specific expression for Fourier's law when we're in cylindrical coordinates. Okay. All right, any questions on this before we do one more example today? Okay, all right, so let's do a simple example of using this 1D heat equation in cylindrical coordinates. All right, and so in this example, we have a hollow cylinder. Okay, and so this hollow cylinder is going to have prescribed temperatures on 2 different surfaces. Okay. Okay. All right. Right. So here is our cylinder. It's hollow. Okay. We'll say that the inner radius of the hollow cylinder is going to be r sub I, and the outer radius is going to be r sub O. Okay. In addition to that, we have the temperatures of the inner and outer surface. Okay. And so the inner surface, let's say, has a temperature Ti, and the outer surface has a temperature TO. Okay. All right, so let's write down our assumptions. And so our assumptions are, first of all, we're going to have 1D, radial heat transfer. Okay. And so we can use the 1D heat equation that we have that we had on the previous page. Okay. We also have, we can assume that our situation is going to be steady state, and so we can get rid of the time term. Okay. And for this simple example, we're going to assume that there's no production as well. Okay, and so our Q dot term is going to go to 0. Right. Let's list out our boundary conditions as well, before we get started. Okay. All right. So this is kind of like the cylindrical version of the first example we did on Monday. Okay. And so we have prescribed temperatures both on the inner and outer surface. Okay. And so our first boundary condition is that T at Ri is going to be equal to Ti. Okay. Then T at Ro is going to be equal to TO. Okay. And for this problem, we're interested in solving for the temperature distribution in the solid part of the cylinder. Okay. Okay. And to do that, we're going to use the heat equation. Okay. All right. Any questions on this? Okay. All right. And so now, now that we've, written out the problem, we can go ahead and try to start solving it. And so I'm going to just, because we're assuming it's one-dimensional, I'm going to go ahead and work directly off this equation right here. Okay. With one additional step, because we're assuming that there's no production. And so I'm going to go ahead and cross out the Q dot term. And so our starting point for this, and if we assume that K here is a constant, then we can pull K here out of the derivative. Right, and so we have ddr times of R dt dr. This is going to be equal to 0. Right, because we got rid of the production term. Right? If we multiply both sides by R over K, okay, we can go ahead and get rid of those terms, right, because we're just multiplying by 0. And then what we get is d dr of R dt dr is equal to 0. Okay. All right. And so now that we have it in this form, we are ready to integrate, okay, because we want to get rid of the ddr. So let's go ahead and integrate this with respect to R. Okay. And then on the left-hand side, what we have is R dt dr. Okay. On the right-hand side, we're taking the integral of 0, which is normally just 0. But since we're taking an indefinite integral, we have to add our arbitrary constant. And so on the right-hand side, we have C1. Okay. Right. And so before we integrate again, we have to divide by R just to kind of get that away from the left-hand side. Right. And so right now we have dt dr is equal to C1 over R. Okay. And so let's integrate this one more time. And so if we integrate one more time, then we get T of R is equal to the integral of C1 over R is the natural logarithm of R. And so we have C1 ln of R plus C2. Okay. And that right there is our general solution. Right. And in order to get our specific solution, we're going to need to apply our boundary conditions. Any questions so far on how we perform the integral? Okay. All right. So unfortunately, the application of the boundary conditions here is a little bit more complicated because, because of the natural logarithm. And so it's going to take a couple more arithmetic steps, but the whole idea is still the same. Right? And so I'm going to go ahead and apply both of the boundary conditions at once. Okay. Because the application of one is not enough to solve for the whole thing. Right. And so if we plug in the boundary condition at r is equal to ri, what we get is C1 times ln of Ri plus C2 is equal to Ti. Next, we're going to apply the boundary condition at Ro. Okay, so we have C1 ln of Ro plus C2 is equal to To. Okay. And so, you can see here that we can't, we can't directly, solve for C1 or C2 outright here. Okay, and so we need to solve both of these equations at the same time. Right. All right. But there is one kind of neat trick with this, because you can see here that C2 appears in both equations like kind of by itself. And so we're going to do a trick here where we kind of subtract both equations from each other to kind of get rid of those C2s at the same time. Right. So you guys have seen this before, right? Where you have a system of equations and you subtract one equation from the other. Does that sound familiar? Great. Awesome. Okay. And so if we subtract these two equations, we can see that we get rid of C2, right? And so on the right-hand side, you get C1 times ln of Ri minus ln of Ro, okay, is equal to Ti minus To, right? And you can see here that since we've eliminated C2, we can go ahead and solve for C1 outright, okay? But before we do that, I'm going to simplify this term a little bit, right? And so maybe you've seen this before. I know that I didn't actually see this until I got to grad school. But if you subtract two logarithms like this, you can actually simplify it into a single expression. And so if you have ln of one thing minus ln of another thing, you can simplify that as ln of the first thing divided by the second thing, all within the same natural logarithm. Okay. And so that left-hand side, instead of ln of R1 minus ln of Ro, is going to be just C1 ln of Ri divided by Ro. Okay. And that just kind of simplifies things a little bit for us. Okay. All right. Any questions on this? Okay. All right. And so if we go ahead and divide both sides by that natural logarithm, we get an expression for C1, right? And so we see that C1 is equal to Ti minus To divided by ln of Ri divided by Ro. Okay. Okay. And so that's C1. And now that we have C1, we can plug this back into, you can actually plug it into either equation to solve for C2. Either equation, by that what I mean is either of the boundary condition equations. Okay, and so let me go ahead and plug that into the second one. Okay. Okay, so we plug it into the second one. What we get is this. Right. And so we get our expression for C2, which is To minus Ti minus To divided by ln of Ri divided by Ro times Ro. Okay. Right. And so that's C2. And so now that we have both C1 and C2, we can plug those back into our general solution here in order to get our full temperature distribution. Okay. And so one common question that I get is, do we actually get the same thing if we plug into either the first one or the second one? And in fact, you actually do. But it is 3:45, and so I don't want to keep you. And so I'll just kind of keep you hanging. And so on Monday when we come back, I'll show you that if you plug in this C1 and C2 back into the original equation, and you do a little bit of algebra on top of that, you can see I'll show you that you get exactly the same thing, for both. Okay. All right. Any final questions on any of this before we wrap it up for today?
Yes, sir. I don't know if you guys want to do it like after class, but I have a question back on like the second page on the convection part.
Okay. Yeah. Let's let me handle that after class then. Let me see if anyone has any questions on the cylindrical stuff. Back to page 22. Yes, I can do that. All right, and so if you don't have any other questions, I'll go ahead and call it here for today. And so thank you guys for tuning in today. Hope you guys enjoyed the rest of your weekend. If you have any questions you want to ask me after class, I'll stick around for a while to answer them. But if not, I will see you on Monday. Thanks, guys.
Thank you, Professor. Have a good weekend.
Thanks, you too. All right, Nick, so you had a question back on page 2 of the notes.
Yeah, it was a convection boundary condition situation.
All right, was it this one or this one?
It was that one. So can you, okay, first of all, hold up. Right under where it says conduction there, the negative q dot over k times x.
Yeah.
You drop that because there's no production in the convection part, right?
We dropped it because we plugged in x is equal to 0, basically, because the convection is occurring at x equals 0. And so, the production term here is multiplied by x squared. And if you take the derivative, it's still multiplied by x as well. And so when you plug in x equals 0, that production term just drops out of both sides of that equation.
Got it. Okay, that makes sense.
Thanks, Ralph.
No problem. See you guys.
I have a question.
Sure. What's up?
So like, if we need to use the restroom, can we just go?
Oh yes, please. Yeah, just go.
I meant like in person, yeah.
Oh yeah. That's fine too. Yeah, if you need to go to the restroom or step outside during the lecture, you can just go ahead and do it. So as long as you're as discreet about it and you're not disruptive, then that's fine.
And if I miss anything, can I just ask you after?
Oh, of course, of course.
Thank you.
Yep. Nick, any final questions?
I guess kinda. Between the lines where we have the conduction equals the convection.
Yeah.
I think I understand that, but going to the next part, the dt over dx, did you just do simple algebra there, or did you like plug in was it Fourier's law?
Yeah. So this dt dx, I just plugged in our general solution here, and so our general solution here is a minus q dot over 2k times x squared plus c1x plus c2. And so I just took the derivative of this with respect to x. And so you do that, you get minus q dot over kx plus c1. So the Fourier's law is actually this entire expression right here. So Fourier's law is minus k times a times dt dx. And then I was just evaluating each of the terms. And so the only one that needed really evaluating was just the temperature derivative.
Okay, that makes sense. And so this is pretty similar to number 2 on the homework, right? Applying this kind of same thought process to the convection part.
Exactly. Yeah. So when you go to do the homework, and I believe on the right hand side, if you're looking at the right side of the plate, the right side of the plate has that convection boundary condition. So this is basically how you would do it.
Okay, sounds good. Thank you.
Yep. All right, have a good weekend.